Okay. Hello, good afternoon. Hopefully you can hear me over the background noise. It's great to see so many people here today. My name is Andy Champ. I'm from GE Vernova, part of the GE Vernova Hitachi nuclear energy team. I'm here to talk about delivering in reality our BWRX-300. For those that are less familiar with GE Vernova, it's relatively new brand, a relatively new name in the market. It was only born 18 months ago. You may be familiar with the larger historic group GE, General Electric, big American conglomerate. Well, 18 months ago, that company was split into three parts. GE Healthcare was separated and is now a separate listed company on the New York stock market. They make all the X-ray machines, CT scanners, and so on. Separate business. The business that makes the jet engines under the aircraft wings, that is also now a separate business, GE Aerospace. And the other third, which is GE Vernova. Vernova being one of those PR terms, brand names. It's a Latin term, mix of new and green, to emphasize our mantra, our mission statement of electrifying and decarbonizing the world. As part of that business group, you can see the capability and the product lines we have in our stable. So we are not just nuclear. We have gas turbines, we have steam turbines, hydro, we have solar, we have battery storage and wind generation. We have grid capacity and digital software that supports many of the national grids, as well as some of our accelerator businesses like GE Financial Services, used to be known GE Capital for those in the finance world. And we have research and a consultancy business. That's all makes up what is now circa $140 billion market cap business in its own right. So substantive growth over the last 18 months. Reflects the growth in the electrification and the demand for energy across the world. And then across that stable, our products have produced over 30% of the world's electricity in that swing. But specifically, I want to talk about, obviously, the conference today is nuclear, so we'll focus in on the nuclear history of GE Vernova. We have a long history, a proud history of building nuclear technology going back over 80 years. So our current evolution of the technology is built on pedigree over that history. You could see the evolution going from the boiling water reactor to the ESBWR to the ABWR and what is now our new product in our stable, which is the BWRX-300. So the acronym BWRX is the boiling water reactor, BWR. The X stands for the 10th generation of that technology, and the 300 is 300 megawatts electrical output. So it kind of does what it says on the tin, as the advert says. Why have we developed the BWRX-300? We still have the gigawatt scale proven licensed technology in our stable. And we do have a joint venture to support TerraPower in the micro stage. But why did we develop the BWRX? It was to challenge some of these issues that the sector has in the marketplace. Many countries around the world really struggle in developing and delivering gigawatt scale projects, both from a financial resource capability and from a physical skills capability. So developing a smaller product means it's more financially affordable, more financeable from a private finance point of view, and therefore more deployable. You can recycle the financing, reinvest, refinance, reinvest, refinance, and so on. So we can repeat this many times over. And that's where we get the economies of scale. Rather than getting the economies through bigger is better, you get the economies through repeat production. So it's more like a product line rather than a construction project. And that's the whole ethos behind SMRs, is they are modular, they are more manufactured rather than constructed in cold, wet weather out in a field. So you get more consistency and quality control in the process. So what we're aspiring to do here is drive down the capital cost, deliver overall a lower cost of energy at the outturn, and generate a certainty in outcome. So if we can move a lot of the manufacturing into factories, the target is to get to 60–70% in a factory, so therefore it's environmentally controlled, it's quality controlled, it's better. You get the consistency and productivity. You increase the certainty in delivery. And as I said, with the LCOE target, then the more you can deliver, the lower that drives down. It's worth saying there's in one of the most recent gigawatt scale projects, Hinkley Point in the UK, it's said to be 1/3 of the cost of electricity coming from Hinkley Point is associated with the cost of financing. So, you know, as well as driving down the construction costs, if you can drive down the finance costs, then you've massively impacted that LCOE. And again, that's why we targeted a shorter construction time to drive down the borrowing costs, which means you can then refinance and drive down the LCOE. So in developing the BWRX-300, we didn't just shrink it and make it smaller, because that would create complexities and access and maintainability and such like. We really revisited some of the safety cases and some of the challenges that we had. In doing so, we've managed to strip out a lot of the equipment that goes into the nuclear classification zone 1. So it relies, as a lot of the generation 3 technologies, it's passive safety, so they reverse the logic on the safety cases, so it's passive safety. And in the worst case scenario, then it relies on natural circulation through the pressure vessel. The valves, circulation valves at the top, default open, and the water floods the chamber, and it works on natural convection there afterwards to allow for safety up to 7 days without human intervention. After that, all you have to do is get a hose pipe and top up the tanks at the top and keep going. So it's built in, passively safe, even if you lose power in the worst case scenario. In doing so, we've reduced the amount of parts and the amount of equipment that goes into the plant. So therefore, implicitly makes it simpler. There's less parts to go wrong, therefore it's more reliable. If there's less parts and less materials in it, it makes it cheaper, and therefore it makes it quicker to construct. Bit of basics in terms of what a BWR is rather than a PWR, pressurized water reactor. A boiling water reactor only has 2 primary circuits, whereas a pressurized water reactor has an intermediary heat exchange loop in the middle, which again adds more parts, adds more complexity, more components, more cost, and therefore less reliability. So we believe that this technology has some huge advantages over some of our competitors, and has been proven, as one of the earlier slides said, there's over 60 of these boiling water reactor types around the world in safe operation. Another reason for designing a 300 megawatt sized unit was to target different user groups. So yes, it can be grid connected and provide grid stability and baseload power to grids, but it can also serve directly data center companies. That's a growing market at the moment. I'm sure we've all heard about the huge demand in data centers there. But it's also been designed to target maybe desalination production or even hydrogen production. It can serve to support CHP. So a number of our clients at the moment are now specifically looking at CHP production to support industry and district heating schemes around. So you can build out a series of module reactors and build up the capacity, and therefore it builds in reliability with multiple units over time. In terms of footprint, you see some rough dimensions of the main power island there. The simple way analogy that we use is the size of a football field, a soccer field. You can fit one of these on a standard football pitch. So the footprint is massively reduced, and therefore it opens up alternate siting opportunities. I've heard it mentioned elsewhere over the last day or two that the target market initially would be existing communities that have nuclear power stations. However, with the size of these plants, it opens up to maybe other brownfield sites, maybe other disused coal-fired power plants, maybe gas-fired power plant sites that maybe could reuse the infrastructure that have got, maybe even other industrial parks that are allowable to this. So opens up a lot more market opportunity. As part of the design, obviously we factor in safety. That's part of the reason why we've kind of semi-sunk the pressure reactor, the pressure vessel. 2/3 of it is below surface. That is consciously designed in to improve or minimize the impact of aircraft impact or other foreign object impacts, make it safer. Sinking a shaft like this is well-known technology for the civil construction industry, so we're not doing anything new or novel in doing that. So it makes it more streamlined, makes it safer, and reduces the novelty factors. The design has been fully designed, as you'll see shortly. This has been done in 3D, but we've also looked at the whole construction sequence and the modularity and how we manufacture components, how we bring them to site, look at the conflict issues inside the plant as we build it. And we've looked at the construction timetables. We've fully resource loaded construction schedules. We've looked at the logistics. We've looked at the manufacturing on site. We have a long history of delivering the BWR reactor types on time, on track, and we plan to fully continue that record with the BWR. And here is reality. This isn't just a 3D model anymore. This is being put into practice. This is the Darlington site in Ontario, in Canada. We are working with our client, Ontario Power Generation, to build the first SMR in the Western world. This is the construction site. This is the shaft where the reactor pressure vessel will reside. We received our regulatory construction license earlier in February this year. So we are now not just doing non-civil construction, non-nuclear construction, we are doing nuclear grade concrete and pouring foundations. Not only that, but we're also manufacturing. The long lead items such as the pressure vessels, the transformers, the fuel are all now in manufacture. So you see the top left are the pressure vessels being manufactured by BWRX-300. The fuel in the top right, that's been manufactured and assembled in our own facility in North Carolina at GE Nuclear Fuels. And you can see the other components, the pressure vessels equally going through their quality control and inspection processes. So this is now real. So what we're hopeful, what we're looking for now is the next projects. Darlington has been consented for 4 units. We're working with OPG now to develop and start the engineering and construction processes for units 2, 3, and 4. We are also talking to TVA, Tennessee Valley Authority, to looking at the siting and the site engineering works in the US. Sask Power, Saskatchewan Power, in Canada. They are in late negotiations, let's say, with ourselves to develop close behind OPG. In Poland, we're working in partnership with Orlon Synthos Group, OSGE. They've now got a site identified in Poland. We are entering into early works agreements with them to start the site-specific design. That particular user group is specifically looking for CHP on the back of industrial processes. So we're doing the site engineering for that with a target of getting financial close later this decade. And then we're in the final down selection process in Sweden with Vattenfall. And we're in a partnership with Fermi Energy in Estonia to deploy 2 SMRs there. And there are many other nations knocking on the door and expressing interest in pursuit of what will be soon a proven product, no longer a theory. So what are we looking for in any new market, any new country to help deploy this? What we need is a teamwork, is a collaboration with a public-private partnership. Yes, we need supply chain. Yes, we need manufacturers and skills and trades and everything. But fundamentally, we need sites, as I mentioned. If we've got nuclear sites that are available, great. If not, then there's other options of coal, gas, other industrial brownfield sites we can look at. But it generally needs a government policy support to identify and support the promotion of nuclear sites in order to win over the public support. Ideally, we'd have international regulatory harmonization. What we're aspiring to do is build a standard product that can be manufactured and exported and deployed across the world. What we're good at in the nuclear industry is having individual national regulations that mean we'd end up with a different plant in a different country every single time. What we need to do is move away from that, and we need standard products that we can manufacture and deploy worldwide, so we truly get a standardized product line. So we need the regulators to talk to each other and harmonize on the outcomes. The early technologies always struggle to get off this ground. We saw this with offshore wind when that first came to the market. Likewise with solar. The first projects of any new technology are never the cheapest, but you've got to stick with it to see the economies of scale come through. You look at the offshore wind market now, and there's thousands of them around the world. Likewise with solar, the costs have come down and deployment. We're hoping for the same in the SMR world. But the initial projects are full with skepticism. And not surprisingly, the nuclear industry hasn't got the best record of delivering on time and on record. So the banks, the investors are a little bit cynical. So we need to challenge that. We need to continue and deliver on time and on budget. But initially, we would aid from having revenue support mechanisms. That could be a CFD from a creditworthy off-take, or it could be a regulated asset-based off-take. But that revenue stream, that visibility of revenue, then gives investor confidence that they can pay back the loans because you know you've got a revenue to do that. So that's a key part, and that's where a government can potentially play a role as well. And the development integration, that's where I say the public-private partnership comes into place. It takes a long time to develop and build nuclear power projects. What we need is some security policy, governmental security, if you like. We don't want to get halfway down the track and then the government's change their minds and say we don't want this anymore. Because that's, not surprisingly, happened in the past. So we'd like to have some level of commitment from government, some policy level commitment to give us that public-private partnership to help us deliver. On the regulatory front, some of the regulators around the world are talking to each other, which is great. There is an international collaboration agreement between the US, UK, and Canada already, and they are actively sharing information and knowledge. So the UK regulator, for example, is learning the lessons from Canada as our safety case submitted there, and was able to go through the UK regulation process in record time as a consequence of having a solid, sound safety case, but the regulators talking to each other and learning the lessons as well. So we'd like to see that repeated more widely. And I mentioned already some of the financial revenue streams that could be available to help us develop those. a RAB, a CFD, a dispatchable power agreement. So none of these are new. They're all mechanisms that have been used for other power generation technologies. So why aren't they available for nuclear? And again, the targeted integration with public support, with government backing that help us, give us confidence, give the investors confidence that they can back the technology and see it through. So that's all I have today. So this is really a reinforcement of saying this is no longer a pipe dream. This is no longer a theoretical PowerPoint of how you build a nuclear power station, because we're actually doing it. We're doing it in earnest. This is real. This is real jobs today. Supply chain opportunities are being created in Canada and hopefully soon elsewhere in the world. Thank you very much.